A solar water heater, hot water heating system consists of a hot water tank and a solar panel. The tank is well insulated and has a time constant of 60 hours. So let's write that down. So K is equal to 1 over the time constant. K is equal to 1 over 60. Okay. And the solar panel generates 2400 BTU per hour during the day, and the tank has a heat capacity of 2 Fahrenheit per 1000 BTU. If the water in the tank is initially 106 Fahrenheit and the room temperature outside the tank is 84, what will be the temperature in the tank after 11 hours of sunlight? So we wrote the Newton's law of cooling for temperature inside the building. In this case, the tank can be considered as a building. And so we have the water in the tank is initially 106. So that's the initial building temperature. Tank is like the building here. So T of 0 is equal to 106. And then the room temperature outside the tank. So that's the outside temperature, which is M in our notation. M is the outside temperature. So M is 84. What will the temperature in the tank after 11 hours of sunlight? So we have to find T of 11. Big T of 11. Okay, so and then the other things in the Newton's law of cooling, H is the additional heating rate due to people, lights, machines in the building. So in this case, building is the tank, and there is nothing additional given in the tank which is causing any additional heating rate. So H will be 0. And then U is the rate of change of temperature due to furnace or AC in the building. Okay, so this one, it's the rate of change of temperature due to furnace or AC in the building. So in this case, it's the solar panel that is acting like the furnace, and the rate of change of temperature will be the temperature unit divided by the time unit. So you should have Fahrenheit per hour. Now, we don't have anything given in Fahrenheit per hour. We are given the solar panel generates 2400 BTU per hour, and the tank capacity is 2 Fahrenheit per BTU. But if you multiply these two quantities and the units get multiplied, you will see that you do get Fahrenheit per hour. So let's do that. So we'll have insert equation. So we have 2400 BTU per hour. So when that is multiplied with 2 Fahrenheit per 1000 BTU, so 2 Fahrenheit, so let's write it as a fraction, 2 Fahrenheit per 1000 BTU, so tau divided by 1000 BTU. Now you see that the BTUs cancel out, and 2400 times 2 over 1000 is 4.8, and we get F per hour, so Fahrenheit per hour. So that's equal to 4.8 F per hour. And so that is the temperature per hour, and that's rate of change of temperature. And that's the rate of change of temperature due to furnace. In this case, solar panel is the furnace, so that thing is equal to U. Okay. So now we have all the data for our Newton's law of cooling. So let's just copy the Newton's law of cooling. And then let's substitute the values. So K would be 1 over 60. So this will be negative T by 60. And this will be T by 60. And 1 over 60 times 84. So 84 by 60. H is 0. U is 4.8. Okay, so now okay, so here 84 over 60 plus 4.8. So let's see how much this will be. This is 1.4. 1.4 plus 4.8 is 6.2. So that 6.2 is a constant. And then the integral of e to the t over 60 would be 60 times e to the t over 60. Plus c. Remember, this e to the negative t over 60 distributes over the whole thing. And then we distribute this. I think I chose the wrong symbol. I meant this to be the brackets. So 6.2 times 60. Well, is it 372? 372 plus C E negative T over 60. Font has suddenly changed for no reason. Okay, so that is T of T. T of T. And then we use the initial condition to find C. So T of 0 is 106. So we use that. T of 0. So substitute 0 is equal to 106. Okay, so CE0, that is just C. And 106 minus 372 is negative 266. So C is negative 266. And now we substitute the C in the equation. Negative 266. And we want the temperature at 11 hours. So T of 11 is to be found out. Let's copy this. Substitute 11 for the little t. Let's calculate this. 372 minus 266 e to the negative 11 by 60. 150.56. $150.56. Nearest 10, so 150.6. Okay, so that finishes section 3.3.